Okay, so we introduced the idea of connected last time, and so let's talk about the real line. So this sort of kind of ties in with kind of foundations and calc, stuff like that. So the first thing we're going to do is we're going to think about what about the reals makes the reals what it is, gives us its topology. And so we want to sort of generalize that. And so we come up with the idea of a linear continuum. So this is just generalizing the order properties of R. So we want simply ordered sets having more than one element, so it's not trivial. And so we come up with this idea of a linear continuum. And it has the following two properties. It has the least upper bound property, which remember means that every non-empty subset that is bounded above has a least upper bound. And also the second thing is that given two elements in the set, so it's in the order, so one has to be smaller than the other, we can put something in between. So these are the kind of like basic order properties of R that are of interest to us in topology. Right. So if we have a linear continuum in the order topology, then L is connected, and so intervals and rays in L. So this is what we want. And so in particular, as a corollary from this, we get straight away that the real line is connected, and so are intervals and rays in R. Right, because we set it up to be. Because the R is a linear continuum. Okay, so how do we prove that? Well, actually, what we're going to prove is that it's true for convex subspaces in the order topology. And recall that a subspace is convex if you have any 2 points in your subspace. One's going to be less than the other, then that closed interval is going to be contained in that subspace. And so basically we're going to show that convex subspaces convex subspaces are connected, and so that'll prove it for us. Okay. So you've already seen the standard way that you prove something is connected. You first off assume that that we have a separation. So remember, a separation means that we have two non-empty disjoint subsets whose union is the entire. Okay, so if we have a separation of our convex set, so what we just do is we choose an element of A and we choose an element of B, right? That's in Y. Y is convex, so therefore the closed interval is in Y, and so that gives us a separation of that closed interval. Well, okay. Now, let's consider the soup of, let's say, A intersected with AB. So we're just assuming that A is less than B. Doesn't know which one. Okay. Now, what are we trying to do? So if this is is indeed a separation, then since we have C here, C has to belong to one of these elements here, right? C is an has to be in that closed interval AB, so it has to be somewhere in our separation. And so we're just going to argue by contradiction. Well, why can't C be here? Well, if C is in here, C is either equal to B or it's going to be between A and B. In either case, because this is an open subset, that means we can put a little open ball around it. So we can have this interval, open interval from D to C in either situation. But D is a better upper bound than C. Okay, so that can't be. So that means that C has to be in this set here. Why can't that be? Well, again, for the same reason. Again, this is an open set here. So now we can put a little open ball around C. So C goes to E, say. And now we use the property that there exists elements between any two elements. And so there's a Z there. But then Z is an upper bound. And so that shows you that C is not an upper bound because Z is an upper bound. Least upper bound. Hang on, let's say. So Z is greater than C, and it's in A, so C is not an upper bound. So in either case, C can't be here, C can't be here, so this is false. We've got a contradiction. They can't equal the whole closed interval AB. Okay, so let's have a look at a couple of examples then. So let's have a look at a couple of examples of linear continuums which aren't the reals. Okay, so let's have a look at the ordered square. So remember, the ordered square is I cross I in the dictionary order. So it's straightforward that it has the second property, right? Because if you've got any two elements in the set, you can put something in between them that would get that from R. So if it's in the same vertical segment, then that's just the same thing as I. So we put a thing in. If they're in different vertical slices, then you can put something here that's in between. So we've got to show that it has the least upper bound property. So let A be our subset, and we want to show that A has a least upper bound. Well, let's have a look at the projection of A then onto the first coordinate. That's going to be a subset of I, and so from the reals inherits the least upper bound. Okay, and so we're going to get some kind of set down there that has a least upper bound. Now, either this least upper bound B, so B is that least upper bound that we have for this thing here. Either B is in A, so either B cross X is going to actually be a part of A, in which case we just look then at the set of elements in A whose first coordinate is B. That again is going to be some set in I. So again, it has a least upper bound, that be C. And B cross C is the least upper bound for the set A. Okay, so we just attack it from both coordinates. The only thing that we have a problem with is, well, what happens if B is not a first coordinate of an element in A? Then we have some element like this, and so what we can do then is use B cross 0 as a least upper bound, because it couldn't be any other element, because if it was like a B prime cross C, for instance, then B prime would have to be less than B, and we get things which are bigger than it. So we can actually explicitly find least upper bounds. So that shows you it has that property. A second example is in the homework I'm going to give for this section. So if you have any well-ordered set, then if you look at the product of that set with the half open interval 0, 1, you get a linear continuum in the dictionary order. Okay, so now we can generalize the intermediate value theorem. So what are we going to do? Say we have a continuous map from a connected space to a ordered set in the order topology. Okay, so we need the image to have some kind of order for it to make sense to have intermediate values. Okay, so if we have A and B are any 2 points in X, and R is a point of Y lying between F of A and F of B, then there exists a point C of X such that F of C equals R. So this is pretty easy to recognize as the intermediate value theorem. Okay, why is this true? Well, we just try and create a separation. Okay, so let's consider this attempt at a separation, right? We go the image of X intersected between negative infinity and R, and F of X intersected R to infinity. So remember, so this doesn't necessarily have to be real numbers. We just use this as notation for rays in the ordered set. It just needs all the elements less than R. Okay, so straight away we can see that they're disjoint because we've done that. Straight away we can see that they're non-empty, right? Because F of A is in this set and F of B is in this set. They're open, right? They're open in the image, right? Because we've just intersected the image with an open set. Okay, So what do we know? Well, we know that X is connected, so therefore f of X is connected. The image of a connected set is a connected set. And so therefore we know that this can't be a separation. So what does it mean for it not to be a separation? Well, it's almost a separation, right? It's just missing f of X equals R. So therefore, there must be something missing from A and B, because A union B is not the entire f of X. So since that's not empty, that means there exists a C such that f of C equals R. So it's actually quite, I think it's an easy proof, but it's a very elegant proof, I think. It's very pretty. It's all this stuff with connectedness, basically, but it's always the same thing, right? You always...
I don't think it was this short. When we proved this in advanced calc.
Did you have the property of connectedness in advanced calc?
No.
So that's, yeah.
I think there was some iterative process or something we used.
Yeah. So that's a nice thing about topology, is that quite often topologies just gets right to the essence of a problem. So you kind of throw away all the irrelevant stuff, and it's kind of like, so the real thing that makes it work right is connectedness. And so you just focus on that. Okay, so you might have seen problems like this, or maybe not exactly this problem, but a problem like it in calc. So let's say we have a continuous map from the sphere to the real numbers. Why must there exist a point on the sphere such that the function is equal on antipodal points? And it's just, there's just one little cute trick that does it for us. Which is define g of x, a new function, to be f of x minus f of minus x. Have you seen this kind of stuff before? I think it's like when you do Rolle's theorem, and right. Yeah, I think actually the way that you prove intermediate value theorem, don't you start off with Rolle's theorem first? That, like, if you've got a positive point and a negative point, there has to be a root. Oh, it's a mean value theorem. Okay. Yeah, okay. So anyway, so this is a continuous map. Why is that? Well, it's the difference of two continuous maps, and this is the composition of two continuous maps. Okay. So that's that. Okay. So just think about what does g of minus x equal? Well, g of minus x equals f of minus x minus f of minus minus x, which is just equal to minus g of x. Okay, so you've got a function that at one point is some value, and at its antipody, it's negative of that value. And they just consider a path then going from x to its antipodal point. Right? That's going to be along that path. you start off at one end, you start off with a negative number, you end up at a positive number. By the intermediate value, somewhere in between, it has to take every value, so it has to take 0 at some point. And if g of x is 0, that means at that point, the antipodal points are equal at that point. And so that's true actually for every path that goes from a point to its antipodal. So in fact, we've proved more than just there's one point, there's actually infinitely many points. So that's it. So that's an old trick that's used a lot in these kind of problems. Okay. Okay, so since I talked about paths, let's actually make that a little bit more rigorous. So given any points in a space X, a path in X from between those 2 points is a continuous map from a closed interval in the real line to X, such that f of A is at X and f of B is Y. So we can actually rigorously define a path that way. And a path is a loop if X equals Y. So, and we say that a space is path connected if every pair of points every pair of points can be joined by a path in X. And actually, it's very easy to set up an equivalence relation between paths. So if this is if the vertical slice is a path, so you can have like a map. So remember, a path is a map from the interval to X. So this thing setting up the equivalence relation, we look at if we let this direction kind of be X, and we can call that direction T, like a time variable. And so then we want f of X of T to be some continuous function such that fx0 is one path, path 1, fx1 is path 2. So here is path 1, here is path 2. If we can, by a continuous map, do this kind of setup, then that's basically what we're doing, is we're continuously deforming this path to this path. And then you can set up an equivalence relation of paths. Okay. Right. So a path is obviously equivalent to itself because we just let it be constant in time. A path, if path 1 is equivalent to path 2, then path 2 is equivalent to path 1. We just flip over this picture. Just go backwards in time. And transitivity just means we just glue one of these squares over here. And so that means we've got then a map going from 0 to 2, so we just go twice as fast. And that gives us an equivalence of paths. So anyway, we're not really going to do anything with this, but if we were doing algebraic topology, this is kind of important in that. If we had time, we would do it, but don't really have Okay. Now, a path connected space is connected, but a connected space need not be path connected. Okay, so why would a path connected space be connected? So let's start off. Let's say we have a path connected space which is not connected. So that means we have a separation A and B. What's the natural thing to do?
Take points in each of those and draw a path between them.
Yep.
And something about continuity is probably
Yep.
violated.
Right, because the separation of the space would give us a separation of the path, but paths, paths have to be connected because they're paths. They're the image of a connected set. So yeah, so it's easy to do, but the fact that a connected space need not be path connected, we'll have a look at a couple of examples of that in a little bit. Okay, let's have a look at a few classic examples of path connected spaces. What about the unit ball in Rn? So I just remind you what the unit ball is. So that means it's the set of x in Rn such that the norm of x is less than or equal to 1. And of course, by the norm of x, I'm using the Pythagorean Euclidean norm, which is square root of x1 squared plus x2 squared, etc. Okay, so to show this is path connected, all we've got to do is come up with a path between any 2 points. So if x and y are any 2 paths, any 2 points in the unit ball, then consider this. Okay, so this is the standard way that you come up with a path in Rn. Right, so when t is 0, you're at x, and when t is y, you're at t is 1, you're at y. And so as you go from 0 to 1, you're continuously going from x to y. And so the only thing you have to check then is that you stay within the ball. And let's just check that. So what is the norm then of 1 minus t x plus t y? What's the standard trick now that we do? Triangle inequality, exactly right. So 1 minus t x t y. And of course, these, now we use the fact that x and y are in the ball. So they're at most norm 1. And so we stay within the ball. Okay, let's just. The punctured Euclidean space. By that, I mean we take Rn and we just remove the origin. That is path connected for n greater than 1. Obviously, if n equals 1, right, then we've got the real line and we've taken away the origin. We can't get then from negative numbers to positive numbers. But if n is bigger than 1, we're given 2 points x and y. How do we go from x to y? Well, we might just try the same trick we did before. What's the only problem then?
What if that straight line, well, what if 0 is collinear with those two, I guess?
All right, and that only happens, right, if that's negative y.
Right.
And then if that's the case, then you just pick some z which is not equal to k times y. And then that means you can do, and that's a good, perfectly good space, a perfectly good path. Okay. Here's another one. The unit sphere in Rn. So I don't know if we've defined it yet, but Sn minus 1 lives in Rn as just the points of norm 1. And again, for n bigger than 1, this is path connected. Right? When n equals 1, it's not path connected, right? Because what does S0 look like? S0 is just the points 1 and minus 1. So that's not very nice. But to prove that Sn, the sphere, is path connected, let's consider the map from the punctured Euclidean space to the sphere given by mapping a vector to the vector divided by its norm. Okay? This is clearly surjective and continuous, right? Because x never equals 0, so we never any problem. And just like we have that the continuous image of a connected space is a connected space, the continuous image of a path connected space is path connected. Again, because the continuous image of a path is a path. So any way that you can go in your domain space, if you've got an image, you can get a path by just pulling back the path to the space you started with. Okay, so that's examples of path connectedness. So let's have a look at a few nasty spaces. Now, spaces which are connected but not path connected. Here's the ordered square. We've already seen that that's, so we know that that's connected, right? Because we can't split up into open sets. But why is it not path connected? Well, let's just say we had a path that went from 0 cross 0 to 1 cross 1. Okay? Then for each x in 0, 1, look at this open interval here, x cross the open interval 0, 1. That is an open set. A path is a continuous map, so its pre-image is going to be some open set in AB, our interval, our closed interval AB. So for each x in the interval, we can come up with a ux. So, and their ux's are going to be disjoint if the x is, if ux is not going to equal, is disjoint from uy if x doesn't equal y. But this is an open set in a closed real interval, so therefore it contains some rational number. So what does that mean? So that means for each point in the interval here, we can assign it a different rational number. So that's an injection from some subset of the rational numbers. It's a surjection. No, what is it? It's a surjection from some subset of the rational numbers to the unit interval. But this can't be, right? Because the unit interval is uncountable and the rationals are countable. So that's a contradiction. That makes sense?
How do you know each x cross 0, 1 is assigned to a different rational number? Or
Right, because for different x's, it goes, we're going to have different sets over here, disjoint sets over here. So
right. Okay.
right, so we've got a collection of open sets here mapping to our interval here. So just by pulling back, so for each x, we can assign a rational number which is disjoint. So that's an injection of the unit interval into the rationals, and that's forbidden. It's also kind of, I don't know if we'll have time for this, but this is, you can think of this path as some kind of space-filling curve, right? So it's something one-dimensional, but it's coloring in this two-dimensional, and that's also going to be, we're going to have problems with that, but we don't have the technology yet to deal with that. Here's another example, which is a great source. In fact, they call it the topologist sine curve. So let S be the set in R2 of x cross sine 1 of x, for x greater than 0 but less than or equal to 1. Right, so it looks like this, and then as it comes here, the period gets shorter and shorter and shorter. And then we also, so if we look at its closure, it's going to be the set S, and the closure here is then going to be some interval between -1 and 1 on the y-axis. Right, because every point here, any neighborhood is going to intersect with S. So that's why that's in the closure. Okay, so the claim then is there's no path then from the origin to some point in S. And so that's what we're going to look at now. Okay, so so let's say we do have a path. So let f of t be a path from the origin to a point in S. Okay, so let's have a look at the set of t such that f of t is in this is on the y-axis. So this is some subset in our closed interval in R. So remember, a path is a function from our closed interval to our set here. This then is a closed set. Right, because it's the pre-image of a closed set. And so there with.
Is that T cross T?
Sorry?
What is that set that T cross T is an element
of 0 cross minus 1 to 1. So it's the elements such that the image is on this closed interval here. So so remember, it's our map that's going from A, B to here. And so the elements such that.
Oh, that's all the T's such that.
Yes.
Okay.
The T's such that. Maybe I'll make that clear. So this is in the domain. So it's a closed set in the domain. Okay. So let B equal the maximum element of this set. Oh, let's call it A. Let's call this set A. Maximum element of A. So since it's a closed subinterval, it has a maximal element. Okay, so here, right, we had a path. A path goes from let's call it, oh, not CD, let's call it AC. Let AC be our closed interval in R that we're sending into the topologist sine curve. And so let B then be the maximal element of A. And so we can think of F now as a function from BC to S. Okay, so it's a path from somewhere on this interval to our point in S. And it has the property that F of B is in that interval, but F of T is not. When T is in BC. So all I've done is, so I've got a path from here to here, say. So all I'm saying is that at some point it has to leave this interval. Okay, and so that's the path that I want to consider when it leaves that. I don't really care what it does when it's on this interval here. Okay, now we can get a contradiction. Because let's have a look what's happening. So let me go here. Okay, so I've got some, so let's think of it. So it's a path is a parameterization, right? So we can think of f of t equals some x of t, y of t. And the way that we've set it up is such that x of 0, oh, I'm calling it BC, but we might as well call it 0, 1. So let BC equal 0, 1. So we can just rescale things so that we're on the unit interval. So x0 equals 0. So it's just saying we're starting somewhere on that y-axis. And what else? We have that x of t is greater than 0, and y of t equals sine of 1 over x of t for t greater than 0. Okay, so we don't care what y of 0 is. Y of 0 is something. We're not caring about what that is. Okay, so the claim is Y is not continuous. So if Y is not continuous, then F is not continuous, and that means F is not a path. And so the space is not path connected. And the way that we can do this, so we're kind of, the problem is we've got T and we've got X. So we've got two variables, right? So let's, so what we want to do is we want to construct a sequence Tn going to 0, right? Such that Y of Tn equals -1 to the n. And that will do it for us, right? Because we've got a sequence here which converges, but the sequence here doesn't converge. So that means Y is not continuous if this is true. And how can we do that? So given n, choose, what is it? Choose a U such that U is between 0 and X of 1 on n. And we want sine of 1 on U to equal -1 to the n. And the reason why we can do that is because of the intermediate, well, that's just true. If we go back to look at the map, so as we get closer and closer here, the sine curve is going up and down at a smaller and smaller rate. So we can find given so T is sort of like going like 1 on n. And so with each 1 on n, we find the X value such, I'm not saying this very well. As n goes to infinity, right, so we've got 1 on n, that's a time thing. Our X is getting smaller and smaller. So at T equals 1 on n, no matter how small, how big n is, however small 1 on n is, we can still find values between values of X between T equals 0 and T equals 1 on n, such that X is any value between -1 and 1. So if n is even, we choose 1, which is 1. When n is odd, we choose 1, which is -1. So we can find an X such that is true. And then we just find, once that is true, we can find, so we can find a U such that sine of 1 on U is equal to -1 to the n. And then our Tn is between 0 and 1 and n. So we can because the actual Tn we want is not the X of 1 on n, it's where the actual max or min occurs. But that's okay because that's going to be less than 1 on n. But it's still going to be positive. So we can do that for every n So that gives us a sequence going to 0. And at each point, we're just sampling, we're alternating sampling the max, min, max, min, max, min. And so by a long way, I'm explaining that that's that. And I think that's the end. That's the end for today. Okay, talk about components next time. So the basic thing is that at some point the path has to leave there, but where does it go to? There's nowhere to go to. There's going to be a discontinuity there.